Welcome back to this next video in which we are discussing maximal ideals. Okay, so we now want to prove the correspondence theorem in the other direction. Okay, so let's now say that we've got some ideal, which I'll call capital I here, which is an ideal of our quotient ring, R quotiented out by the ideal capital I1. Okay, so I here is now going to represent an ideal of our quotient ring R by I1. Okay, and what I want to now prove is that I can go from an ideal of the quotient ring to some ideal of the ring capital R, which contains the ideal capital I1. Okay, so what I want to find is some I2 which contains I1 and is itself contained in capital R. So really what I want to find is this I2 here. Okay, so I want to prove that if you start off with an ideal of the quotient ring, that you can always find an ideal capital I2 which contains the ideal capital I1, and which is an ideal of the ring capital R. Okay, so to draw a picture then for what we're going to do here, so let me firstly start by drawing the ring capital R here. So that this is going to be our ring capital R, and as before I will colour in anything to do with the initial ring capital R in orange here. So here's our ring capital R here. Now let's add on to that picture the ideal capital I1 which we're using to quotient out by. So let's say this is capital I1 here, and we'll have capital I1 coloured in pink here. Okay, so there's the ideal that we've quotiented out by, and now of course when we do construct the quotient ring of R by I1, what that will involve doing is partitioning up the ring capital R into the additive cosets of this ideal capital I1, like so, okay, and those cosets will now be the elements in the quotient ring. Now if we've got some ideal capital I of the quotient ring, that is going to be fundamentally a subset of the cosets, okay, which happens to be an additive subgroup in the quotient ring and also closed under multiplication by any element of the quotient ring. Okay, so let's add that onto the picture then. So I here, and I'll denote I in green, is going to be a subset of the coset. So it might look like this basically. It's lots of cosets of I. So in this case I've got 3 cosets here that are all together in this subset capital I. So this is what you should think of I as being equal to. It's a subset of the quotient ring, so it's a set of loads of cosets of the ideal capital I1 in the ring capital R. Okay, right, so now what I want to do is construct this ideal capital I2, which is an ideal of the ring capital R, which contains capital I1, and hopefully it should be pretty intuitive to you how I should do this. Okay, so let's try and do this now. So the way I'm going to do this is I'm just going to union together all of the cosets that are in the subset I. So I, it's a subset of the quotient ring, so it contains cosets. Its elements are cosets. So for instance, it's going to contain the additive identity. If it's a subgroup, it will contain the additive identity coset, so it will contain 0 bar. Okay, let's give some of these other cosets names. So let's say this one contains A, and therefore we can call that coset A bar. Let's say this one contains B, so we can call that coset B bar. Okay, so this ideal capital I, it's it's an ideal of the quotient ring, so its elements are cosets, okay, not the actual elements of the ring capital R. Now, I2 is going to actually be an ideal of R, so it's going to have to contain elements of R, and the way we're going to get it is we're going to union together all of the cosets that are in I. So all I'm going to do is union together all of the cosets, so I'll just write this like so, union, and then I want all of the cosets, so I'll put cosets in I. Okay, so in the context of this picture, you just union together the 0 bar cosets. You take all the elements in this coset, you'd add on all the elements in the coset A bar, and all the elements in the coset B bar to create a big subset of our initial ring capital R. Okay, so that's what I'm doing here to construct this new ideal capital I2 in this way. Okay, so that's how I go from my ideal of the quotient ring to my ideal, or what I claim is an ideal, of the ring capital R. And now it's my job to prove that if this is a ideal of the quotient ring, that this will be an ideal of the ring capital R, okay, and that it will contain I1. Well, hopefully it will be intuitive that it will contain I1 because it has to contain all of 0 bar, and 0 bar is exactly equal to I1. Okay, so what I now want to prove then is that this is indeed going to be an ideal of the ring capital R. Okay, so to do that then I need to prove that it's an additive subgroup, and I also need to prove that it's closed under multiplication. So let's do this. So let's start off with additive subgroup. Okay, so again we only need to check axiom number 1, axiom number 3 and axiom number 4. Okay, so we'll start off with axiom number 1, closure. Okay, so that means that if I take two arbitrary elements from this subset, and I hope you'll agree this is a subset of the ring capital R, okay, so it fulfills that first thing that an ideal is going to have to agree with. Okay, so now what we just need to make sure of is that it's a special subset. Okay, and the first thing we need to make sure of is that it's closed under addition. So what I need to show is that if I pick two arbitrary elements from this subset, so let's just say that I pick A and B, which are two arbitrary elements from the subset capital I2. Okay, what I now need to do is prove that if I add them together, and this addition is in the ring capital R, so this is addition in the ring capital R, that when I add them together I end up with something that's back in that subset. I never end up with something that's outside of the subset. Okay, so how can I prove this? Well, I've got to use somehow the fact that I is an ideal within the quotient ring, because that's all I've got to go on. Okay, so how am I going to use that? Well, of course, if A and B are in this ideal capital I2, or this subset capital I2, we haven't shown it's an ideal yet, okay, that will mean that they were contained within some coset that was in this ideal of the quotient ring capital I. Okay, and we're going to use that fact now. So A will have been in some coset, which we can call A bar, we might as well name it after this element A, and B will have been in some coset B bar, and both of these cosets will be within this ideal capital I, which is an ideal of the quotient ring. Okay, so that's perfectly fine. If those are in this subset capital I2 that we've constructed in this way, then they must have been in cosets that were in the ideal capital I. Okay, so now what we can do is we can consider what was A bar plus B bar, where this addition is addition in the quotient ring. Okay, well, what we know is that this ideal was an ideal. Okay, so when we add any two cosets together, it has to be something else that's back within the ideal capital I. So whatever this answer is, it was going to be back within the ideal capital I. But how is addition defined in the quotient ring? Well, of course, you take a representative from here and you take a representative from here, add them together in the initial ring, and then take the coset that contains the answer. So this, we can think of this as take the representative A, take the representative B, add them together in the initial ring, and take the coset that contains that. Okay, so where this now is addition in the initial ring. Okay, and that coset must have been in the ideal capital I. Okay, but now that tells us exactly what I want to know, because if the coset that contains A plus B was in the ideal capital I, then that now means that A plus B is going to be in this subset I2, because I2 is exactly just the union of all of the cosets that are in I. Okay, so it will contain any element that's in one of these cosets in the ideal capital I. So that's how we've done this. Okay, and it might seem a little bit of a sort of difficult thing to intuitively come up with, okay? It might seem a little bit sort of indirect, but this is the way that we're going to be proving a lot of the axioms that we're going to need to prove in order to prove I2 is an ideal, so you'll get used to this. Okay, so we've just used the fact that I was an ideal of the quotient ring, and that was the thing that we used to construct this subset I2 here. Okay, so we now have proven that I2 is closed under addition. Okay, so we don't need to worry about associativity. Any subset with the restricted addition law from the larger ring will obey associativity. Now what we can worry about is axiom number 3. So axiom number 3, we need to show that the additive identity 0 in our larger ring is an element of the subset. Now why is that going to be true? Well, if I here was an ideal of the quotient ring, then one of the elements that has to be in there is 0 bar, because if it was an additive subgroup, it had to contain the additive identity of the quotient ring. Okay, and the additive identity of the quotient ring is the coset that contains 0. So that means that when we construct I2, you will absolutely always end up with 0 in there. Okay, because I2 is just all of the elements that are in the cosets in I. Okay, so indeed the additive identity is going to be in that subset. Okay, now axiom number 4, we want to prove that we have additive inverses. So let's say we have an arbitrary element A which is in I2. What I want to prove is that its additive inverse is also in I2. And here again I have to use the fact that I was an ideal in the quotient ring. Okay, so if A was in I2, then what we know is that the coset that contained A bar was in the ideal capital I. Okay, so we can instantly conclude that. Now, because the ideal capital I was an ideal in the quotient ring, then we know that it will have had additive inverses for all of the cosets. Now, the additive inverse of the coset A bar is the coset that contains the additive inverse of A in the initial ring capital R. So it's negative A bar. So what we can now conclude is that negative A bar was an element of the ideal of the quotient ring capital I. But then what does that mean? That means that negative A would be an element of capital I2, okay, because I2 is defined to be all of the elements that are in all of the cosets in the ideal capital I. Okay, so indeed it will be closed under additive inverses. We will have additive inverses. Okay, so this is all looking very good. We now have proven all of the axioms that we need to prove to make sure that it's an additive subgroup. We don't need to worry about commutativity. That one will follow from commutativity of the larger ring trivially. Okay, so those are the only 3 that we need to show. Now what we need to worry about is closure under multiplication by the larger ring. So now what I'm going to do is take an arbitrary A from my subset capital I2, okay, and I want to also take an arbitrary, let's say, little c from the ring capital R, and I want to prove that c times A is going to be an element of capital I2. Okay, so this is what I want to prove. I want to prove it's going to be closed under multiplication by the larger ring, and if I do that, I will prove that it's an ideal. And remember, we're working with a commutative ring, capital R, so we don't need to worry about having it both ways round. We only need to do it one way, and then of course the other way will give the exact same answer, so we don't need to bother. Okay, so once again, if A is an element of capital I2, all we can use is the fact that then, okay, A bar, the coset that contains A, will be an element of our ideal capital I. Now C, whatever it is, will be in some coset in the quotient ring. Okay, so C bar will be an element of the quotient ring capital R over I1. Okay, all elements of the ring will end up in some coset, so there will exist a C bar here. Okay, so A bar is a coset that's specifically in the ideal capital I. C bar, more generally, is just a coset that we know has to be in the quotient ring. Now what we can do is consider, okay, what is C bar times A bar in the quotient ring? Okay, well the way, of course, that you do that is you take a representative from both of these cosets here, multiply them together in the initial ring. Okay, and I should stress, this multiplication here is in the initial ring. Okay, and then take the coset that contains the answer. So let's pick useful representatives. Let's pick C and A as our representatives. We multiply them together in the initial ring, so I'll put an orange dot there to represent multiplication in the initial ring, and then take the coset that contains that. But the fact that this was an ideal in the quotient ring tells us that this has to be a coset that is back in I, because we've taken some coset in the quotient ring and multiplied it by a coset in our ideal, so we had to end up with another coset that was back in the ideal capital I. So this coset here has to be in the ideal capital I, but then of course that means that anything that's in this coset will end up in I2, so C times A will be an element of capital I2. So indeed, this subset of our ring capital R is indeed an ideal. Okay, so there we have it. We have proven now that we can take an ideal in our quotient ring and use it to construct an ideal in the initial ring, and this ideal will absolutely always contain the ideal capital I1, and the reason is that one of the cosets that will always be in an ideal of the quotient ring will be 0 bar, and that's just exactly equal to I1. So when we construct I2 in this way, we'll end up with all the elements of I1. Okay, so I2 will contain I1. I1 will be a subset of I2. Okay, so there is this utter correspondence between cosets that are in between I1 and the ring, and the entire ring, and cosets of the quotient ring. Okay, you cannot have an ideal, and ideals in the quotient ring. Okay, you cannot have an ideal in the quotient ring that doesn't have a corresponding ideal that's in between I1 and the ring, capital R, and you can't have an ideal in between capital I1 and R that doesn't have a corresponding ideal back in the quotient ring. They're in utter bijective correspondence. Okay, so now let's go back and prove the theorem that we wanted to prove, and it's really very easy now that we've got the correspondence theorem, so let's go down here. Okay, so what we want to do then is we want to take a commutative ring, capital R, and quotient out by a maximal ideal. Now what does that mean? That means that there is no ideal in between the ideal M and the ring, capital R. So now by the correspondence theorem, that means that there can be no ideals in this quotient ring except for the unit ideal and the 0 ideal. Okay, the 0 ideal corresponds to the ideal M, and the unit ideal corresponds to the ideal R in R. Okay, so if I draw a picture of this, here is our whole ring, capital R, here is our maximum ideal, capital M. We will then partition up R by the additive cosets of M to construct the quotient ring here, which will be these additive cosets of M. And I claim that this can only have two ideals now, the 0 ideal and the unit ideal, and the reason is that if it had another ideal that was a proper ideal, then there would be another ideal. I can use the correspondence theorem that we've just proven to say that there would be an ideal capital I2. So let me say, if there was some ideal that was not the unit ideal and was not the 0 ideal in my quotient ring, then what I could do is now construct this I2. Okay, and if this was a proper ideal in the quotient ring, i.e. not the 0 ideal and not the unit ideal, then that would mean that I2 would have to properly contain, well, in this case, I1 is M, so I'll replace that with an M, and it would also have to be properly contained in R. Okay, so because that's a contradiction of this being a maximum ideal, there can't be any ideals in here other than the 0 ideal and the unit ideal. And just to nail this point in, I'll point out once again that the 0 ideal will correspond to the ideal in R, which is the maximum ideal. Okay, so the maximum ideal in R, this ideal M here, that will correspond to the 0 ideal in the quotient ring, and the entire ring, the unit ideal of R here, which contains M, that will correspond to the unit ideal in the quotient ring, but there can't be any others, otherwise it would contradict M being a maximal ideal. Basically, you can't have any other proper ideals in the quotient ring here, otherwise there would be a corresponding ideal that was in between the maximal ideal and R, and it properly contained M and it was properly contained in R, and that's a contradiction of M being a maximal ideal in R. Okay, so that then proves that this structure that we will end up with will be a commutative ring that only contains two ideals, the 0 ideal and the unit ideal, and we know that any commutative ring that only contains those two ideals is a field. Okay, so now we can conclude that this is indeed a field. Okay, now it also works the other way around, so if you have a commutative ring, capital R, and you quotient it out by some ideal, capital I, and you get a field, so let's say the answer you get here is a field, then you can instantly conclude that the ideal that you had quotiented out by was a maximal ideal. And the reason is that if this is a field, then we know that it has only two ideals. It only has the 0 ideal and the unit ideal. Okay, and therefore back here, the only ideals that are in between the ideal capital I and R can be the ideal capital I itself and R. Okay, because if you had something else, if you had an ideal in between these, okay, then it would have a corresponding ideal over here, and there are no such corresponding ideals over here because it's a field. Okay, so that then shows that this ideal is a maximal ideal. So I hope that's clear. As soon as you've got the correspondence theorem, this is very, very, very obvious. Okay, and I'll stress as my final point that the correspondence theorem is also called the third isomorphism theorem of rings. So if you hear people talk about the third isomorphism theorem of rings, you now know what that means. It means this correspondence theorem. Okay, and with that we will end this video on maximal ideals.